welcome to the next session of this morning. We're going to have 4 talks in this session. And the first one will be given by George Booth, who already shared his slides up here. It would be nice if you could aim for about 25 minutes of the talk, such that we have some time for discussion. So please, George, the floor is yours.
Great. Okay. Can you hear me? Yeah. Okay, great. Well, thanks, Thomas, for the introduction, and thank you for the organizers of this for inviting me. I'm somewhat of a, an interloper, an external member to the Open Mulcast developers, as I'm not actually a developer of Open Mulcast, and so that gave me a bit of pause for thought as to what I should actually talk about. And so I've kind of tried to give a bit more of a conceptual talk, sort of very light on the details, but hopefully gives you some food for thought, and describing some of the directions that we're thinking about going in my group, specifically with 2 members, Charlie Scott and Max Nusspickel. And the kind of conceptual questions I want to pose are very much to do with active space methods and their future as we kind of target ever larger and more complex systems. And that's very relevant to the Open Mulcast community, because one thing that they've really been pushing and pioneering and developing and is really their kind of multi-reference quantum chemistry approaches. And so, hopefully this will be of some interest and relevance. But before I go on to that, just quickly a little plug for another project. Going on the last day and seeing the other talks, a lot of people doing a lot of really exciting work in photochemistry and looking at excited states, excited state dynamics. I just wanted to give a plug to another project, a new method that we've been developing called auxiliary Green's function theory, which is a complete misnomer because it's not a Green's function theory. It's a wave function based method, but inspired by Green's function theory. So it's entirely non-state specific. It calculates the full spectrum with hopefully a kind of a similar level of accuracy for all of your excited states, and it calculates energetics and dynamics all on the same footing. It's kind of based on a renormalization, a renormalized perturbation theory, hence the kind of second order Green's function theory part of it, but it's also got a non-perturbative truncation, which is critical for the accuracy and the efficiency of the method. So if you're interested, check out these papers. It can handle moderate correlation, and it has an n to the 5 scaling up to about 1,000 orbitals relatively easily. And kind of what we find is over quite large test sets kind of is outperforming ADC approaches certainly for charged excited states at least, and kind of gives similar levels of accuracy to kind of equation of motion coupled cluster across this test set. So do check it out. It's also available in PySCF. You can just a very simple sort of Python interface. You can just download and just run that and get excited states. But what I want to really focus on is kind of active space approaches, and kind of, just thinking about 2 directions that have been kind of pursued in recent years is really the ability to target and solve ever larger active spaces. We heard earlier on in this workshop of staggering developments that have allowed us to go up to kind of 22 active spaces in 2 hours per CI step, which was pretty impressive to me. But also kind of, these more approximate but yet systematically improvable approaches, DMRG, SrTiO that we've already heard about today, and that kind of I'm working on in other projects as well. Also selected CI approaches, even quantum computing type approaches that are hopefully going to take us to larger active spaces. And also kind of new regularized multi-reference perturbation theories. So I want to think about these, but also kind of a few more in the context of kind of more fundamental questions. And these are not new questions. These are questions that are often asked. How do you pick your active space, right? This is a question that comes up again and again and again. There are a few kind of automatic ways to pick active spaces that have been proposed in the literature, but they're not still, fully widely used. Still, we have to think about, energetic criteria, chemical intuition, locality, those sorts of questions. And then if we want to have a kind of systematically improvable way, kind of the only approach we've really got is to either improve the level of the perturbation theory we're doing on top of it, which is quite difficult to do, or to enlarge the active space, which is again not very systematic. Then there is kind of fundamental questions about the suitability, the fundamental suitability of the physics that's being captured by multi-reference perturbation theory as we target ever larger systems. And there's this kind of old trope that more is different. Is there new emergent physics that isn't captured by our standard approaches to MRPT as we go to larger systems? And we can kind of take that to an extreme. What about truly infinite systems? Imagine we're doing a real periodic crystalline system. What is the prospects for active space approaches and multi-reference perturbation theories in the solid state, right? Does that make sense? Or when we go to larger systems, is there going to be new physics that means that these aren't the right approaches or that they need to be adapted in some way? And so these are kind of the questions that kind of are driving this talk and some of the developments that I'm going to talk about. So what if we were to take a solid state system and just do a naive construction of a CAS space? Well, let's say we do some kind of mean field calculation on a small simulation cell of a solid, put periodic boundary conditions on it, and we get a set of molecular orbitals. And then we could just define some CAS. We could take some energy window and say these are our orbitals in our active space, and we could do our multi-reference calculations. But then what we need to do with solid state calculations is we need to converge the finite size effects. So we need to take ever larger copies of our unit cells, or in kind of, condensed matter speak, we need to increase the K-point resolution of our cell, right? So we increase the number of K-points. And what this means is that we will end up getting more and more states, necessarily more and more states within that given energy window. So if we just took a purely energetic criterion, as we converge the finite size effects for the same resolution in an energy window, we would end up with more states in our CAS. And so that's obviously not an approach that we can take. That's not an extensible approach to kind of strong correlation in solids. So in some ways, we're going to have to exploit locality in larger and larger systems, or in solid state systems, such that we have an active space that doesn't grow with our system size. But we also, from my perspective, we don't want to have to rely on the localizability of our mean field orbitals, right? As things like our polarizability gets larger, as our HOMO-LUMO gaps get smaller, the ability to localize orbitals to physically or chemically meaningful areas of the active space gets more difficult, both from a numerical perspective, but also because there are fundamental limitations to how local these orbitals can be. We also want a way that we can construct an active space that has genuine systematic improvability, but also is able to span these centers of strong correlation that we think are important. Now, one caveat I want to say here now is I'm going to try and use the kind of language of active spaces, but really what I'm going to be talking about is quantum embedding, right? And that's just it's in some ways, in many ways, it's just a different perspective on the same problem, right? How do you construct an active space? That certainly in solid state communities or even quantum chemical communities more recently is being cast as a quantum embedding problem. Now, what are the differences in some sense between kind of quantum embedding and normal kind of active space approaches? Well, there are two important points. There are others, but there are two important points that I'm going to completely gloss over in this talk in the interest of time. One is that in general, in a quantum embedding, you will completely fragment your system and you will have lots and lots of different active spaces over your system. And then in some way, at the end, you need to combine the results of all these different active spaces in order to calculate kind of global expectation values, energies, and things like that. I'm not going to talk about that. It's very important. We're doing a lot of research in the best way to kind of combine different sort of active space solutions over different degrees of freedom, but I'm not going to talk about that here. And the other is a self-consistency. This is optional, but is something that is generally done when you talk about quantum embedding, but it's not essential. And so we're going to skip that detail in this talk. So I want to talk about quantum embedding. I want to start with kind of an exemplar kind of molecule here that I want to do some kind of sort of multi-reference treatment on, and I don't really know where to start, right? What makes this a quantum embedding, right? We've already heard in this workshop people doing excellent research on things like embedded cluster models, QMMM, kind of continuum environment models. What makes this a quantum embedding is that we're going beyond simply an electrostatic embedding of degrees of freedom, right? So what does that mean? It means that if I want to fragment my system into sort of chunks, I'm going to allow these chunks to be entirely arbitrary. I'm not going to rely on them being, for instance, orbitals that are solutions of some mean field Hamiltonian. I can take these chunks to be truly atomic local orbital degrees of freedom, right? And that means that in the mean field picture, they're not closed quantum states. They don't have an integer number of electrons in them. And so we have to treat them as open quantum systems. And that means that we have kind of quantum, one way to think about it is quantum fluctuations that go from our fragment of interest into its environment. And right, from a kind of more physicsy speak, we're talking about charge and spin fluctations. We're talking about quantum entanglement, quantum information. But in kind of a CI type picture, we're just saying that there are going to be sort of many slated determinants which have some degree of overlap with these states, but are not fully orbital localized within these fragments themselves. So we have to treat them as open quantum systems. And then quantum embedding just basically asks the question, if I take some arbitrary chunk of a quantum system, how do I describe its fluctuations into the environment? How do I approximate those fluctuations and compress them into a set of degrees of freedom, into a set of additional orbitals that span the environment, such that I can then combine those orbitals in the environment that are suitably chosen with our fragment orbitals to define an active space. So it's just, in some ways, you can think about it as a different way to kind of think about trying to construct an active space from starting from an inherently local approach. So let's think a little bit about how we can start to describe these fluctuations, this entanglement that some truly atomic local degree of freedom has with its environment. And what we want to do is we want to assume we're starting from a known wave function, right? And this kind of gives us a kind of DMRG type perspective. So in DMRG, they often have little diagrams like this, and they talk about Schmidt decompositions. Schmidt decompositions are nothing other than a theoretical tool to take a wave function and then calculate exactly what these states in the environment need to be to describe these quantum fluctuations. And they calculate the minimal number of states in the environment that you need to couple an arbitrary fragment to in order to describe these kind of long-range fluctuations. How do you do this in practice? Well, you take a density matrix, you project it into the environment, and then you diagonalize it. And the largest eigenvalues of that environmental density matrix define your fluctuation space, the degrees of freedom that you need to combine with your fragment such that you get back your properties defined by your original wave function. And DMRG starts from this premise. It builds on it a lot more. It does it sequentially, and there are truncations and things like that. But that's the general premise. It's a n-body density matrix in some sense that you diagonalize. I mean, you don't do this in practice, but this is kind of conceptually a way you could do it. It's an n-body density matrix that you diagonalize, and so your states in the environment are many-body states. And then in 2012, Chan and Knizia, they developed this density matrix embedding theory, where they said, okay, let's imagine that our state is not an arbitrary quantum state, but it's a mean field state describable by a single slated determinant. And then we can take our atomic local fragment, we can do the Schmidt decomposition, and what comes out are environmental states that describe the coupling that are one particle states. So they're just orbitals in the environment. And that gives us a way then we can create active spaces. So you construct your active space from an arbitrary local fragment, not one localized from a prior mean field calculation, but an arbitrary local fragment. And then you find the degrees of freedom in the environment that need to be combined with it such that you get back a mean field description over that arbitrary fragment. And this has been expanded on by a number of groups as well as ours. But this is not a new idea, right? I want to make the connection to something else in quantum chemistry, pair natural orbitals, right? In some ways, pair natural orbitals can be thought of as a Schmidt decomposition. In that way, you take an occupied orbital pair, you take as your level of theory your wave function from MP2 theory, and then you think of your environment to just be the virtual space. So you diagonalize the virtual block of your one-body density matrix constructed from MP2 theory as your environment. And that gives you a set of virtual orbitals, which are in some sense most optimally describing the fluctuation space at the level of MP2 from an occupied orbital pair. And that's then the basis of local correlation in the work that's really was pioneered by Mayer, but now being taken onto new heights in Orca with the LPNO code of Frank Neser. So, you know, these concepts are things that come up time and again. So let's think about this in terms of a quantum embedding, but really thinking about it through the lens of active space approaches when we're trying to actually construct an active space for a truly infinite system. So this is kind of a graphene sheet, and I pick a single carbon atom, right? And that takes away any ambiguity about exactly, you know, what I want to define as my fragment space. I'm just going to say that in all the work that I'm discussing here, our fragments are just going to be the atomic valence orbitals of a single atom, right? So here it's just the atomic valence orbitals of a carbon in a graphene sheet. And then I'm going to use my sort of DMET type prescription. I'm going to say, okay, I've got a mean field state over the entire system. What orbitals do I need to include with the atomic orbitals on my carbon atom, such that I end up with an active space which has a kind of a good number of electrons. Essentially, I can construct a Fock matrix in this active space and diagonalize it with a good number of electrons and end up with something that looks like a conventional active space that has a, you know, a reasonable or rather a correct zeroth level description at the level of mean field theory over my fragment. So that's what we can do. That gets us an active space. But then there's a question: how do we systematically improve that active space? One thing that I didn't say is this prescription here only gets the same number of orbitals. This is mathematically provable. The same number of orbitals describing your DMET bath space as it does your fragment orbital. So how do we systematically improve that active space? Because at the moment, it's only considering mean field physics and the local untruncated degrees of freedom of your fragment. One way to do it is expand the fragment size. I'm not going to go down that route. There are many reasons why I think that is not the correct way to go. So what I want to do here is I want to combine the two approaches that I've already mentioned, these ideas of quantum embedding with the ideas of local correlation, and specifically inspired by pair natural orbitals, right? So we've already said that this is capturing this DMET bath space, which augments our fragment space to create our active space. What happens if we now take approximate density matrices from the level of MP2, as you would in pair natural orbitals, project that into the rest of the environment and diagonalize that, and then we can get a systematically improvable bath space, which allows us to systematically converge this longer range correlation. And so if we do that, we diagonalize these environmental density matrices now at an approximate MP2 level that only describes these fluctuations from our fragment of interest into the environment, we end up with a continuum of long-range environmental bath orbitals where the eigenvalue describes how important these states are to describe the fragment at the level of MP2. So we can then truncate this parameter in very similar way to what you would do within DMRG. And we end up with a systematically enlargeable active space that is inherently local, built on this idea of it supporting the description of a atomic local degree of freedom. So we end up with a fragment-specific active space construction. So this is an example here of a graphene sheet. I'm taking as my fragment the atomic valence orbitals on this central carbon atom. And as we change our truncation level, this just describes here now the kind of density of the active space that we're describing. And you can see that it kind of expands out as we allow ever larger long-range fluctuations to be described, but we can also cut things off. And so this is kind of, in some ways, a systematic way for an active space construction that actually works for extended systems. There's a little asterisk here by active space, because what I'm describing is this active space. It is worth kind of stressing that it can be divided into two sets of orbitals that are truly local, these fragment orbitals, that they're the key degrees of freedom that I want to describe. And the rest of the orbitals describe some kind of fluctuation space into the environment that is required to support the description, to get the right quantum description over your atomic degrees of freedom. So let's put this all together quickly before we move on to thinking about MRPT type ideas. This is a very simple example. Let's take an alkane chain, this classic example for kind of local correlation methods, but I should stress this isn't a local correlation method in the kind of framework of a pair, a pair correlation method like coupled cluster. Because these describe the entire excitation space of your local degrees of freedom. There's no explicit truncation in terms of that local excitation space. So it's not limited to coupled cluster level of theory or a pair double excitation kind of description. Despite that, I'm going to start off by using coupled cluster as my active space solver. And the reason for that is that I can then go to very large active spaces and show that this construction really does systematically converge. So I'm going to look at alkane chains. I'm just taking as my fragment individual carbon atoms. And what I find is, as I change this tolerance for the cutoff of these bath degrees of freedom that I'm describing, these environmental fluctuations, if I look at the correlation energy per electron, as I grow my system, you can see that I can very rapidly converge to the coupled cluster level of theory, which is the right limit, given that I'm solving these active spaces with coupled cluster level of theory. Yeah, up to the point where I can kind of canonical coupled cluster conks out, because it's reached its limit, and we can go beyond that because these are only local sized active spaces. And you can see that as we grow our alkane chains, you can see that the maximum active space size does get saturated quite quickly. It obviously grows as you increase the cutoff, but it then doesn't have a dependency with the overall system size. Okay, but you should always be very skeptical of anyone that talks about some kind of local correlation in essentially a quasi 1D chain. Questions are, this is total energies. Do you get consistent accuracies across energy differences? What about going to higher dimensions, more compact systems? And what about stronger correlations, right? So a more compact system, this is Diamond, a condensed phase system. I have got a lot of molecular calculation results, but they're just not quite as polished. So this does all work for molecular systems as well. This is again showing that in Diamond, a compact system with cutoff, the size of your active space does saturate quite quickly as we go to larger and larger repetitions of our unit cells, up to 666 K-point samples, or this is the total number of orbitals in the system. And we can kind of systematically converge the energy with respect to this cutoff. And then we can do this for kind of equations of states, right? So we change the we change the volume of this unit cell, and we look to kind of converge the equilibrium lattice constant with respect to this truncation threshold. And you can see that the results we get are very close to experiment and well inside the scatter of literature DFT results. So we're quite confident in these ability to kind of systematically converge these results. And we can do it for other structural properties that we can calculate from the energetics, things like the bulk modulus. One thing to note, and this is the first time I think this has ever been applied in a solid state system, is that we actually do counterpoise correction as well, which is very important to account for the basis set superposition error, which I don't think has ever been applied within a solid state system, but it's something we found that was important. Then we can do the same for things like graphene, where we expect really long-range correlations. And we were really surprised this works as well. But again, we're inside the kind of experimental uncertainty and the scatter of density functional theory results. And we're quite confident in terms of the convergence with respect to this bath truncation. We can go to stronger correlations. This is an active space approach, as I said, that's not limited in terms of the truncation level. We can do things like tailored coupled cluster, which is sort of a quasi-strongly correlated method. It's kind of fundamentally still based on a single reference coupled cluster, but we essentially can do then sort of full CI in our fragment plus a small part of our bath tailored, which tailors the coupled cluster over the larger fragment. We can compare with kind of approaches from hybrid functionals and other type of empirical results for strongly correlated perovskite systems. Again, getting very good agreement with experiment. And this is quite a nice little example of a system that I've been doing with Ivan Runga from the National Physical Laboratory. They're developing these pollution sensors that are essentially absorbing single molecules of NO2 on graphene sheets. And all of their standard density functional theory predictions are completely wrong for how this NO2 binds to graphene, essentially because there's delocalization error and self-interaction error, which means that whenever you look at these NO2 molecules absorbing on this graphene sheet, the LDA or any density functional theory will always transfer partial amount of its charge onto the graphene sheet, which is not what they know is happening. It's either transferring no charge or it's having a complete charge transfer of an electron from the molecule to the graphene sheet. So as a function of gate voltage, essentially the relative energy levels of the NO2 compared to the graphene sheet, we can see this discontinuous behavior as it transfers a whole electron, as it should do, from the NO2 to the graphene sheet. But I want to go on to talk a little bit about multi-reference perturbation theory, right? So what we've got here, and I've you know, I just sort of touched on the results, and I haven't really gone to too much more sort of strongly correlated systems, but it's a way at least to start from an entirely local picture and build up an active space approach in extended systems. But the active spaces are quite large if you really want to systematically converge that physics. And is that really the right approach? Is it a systematic expansion of the active space really the right approach to converge the physics? And from a sort of multi-reference quantum chemistry perspective, you'd say no. Well, you don't really try and converge the active space of your molecule. What you do is you do some multi-reference perturbation theory for the dynamic correlation on top of it. And that's really what we're trying to converge, because we have no knowledge of the interactions outside this active space description that we construct. But I want to sort of talk briefly about a kind of different perspective that comes more from the condensed matter physics side of things, that I think is a physical process that is being missed, even in multi-reference perturbation theory, right? So if we take our fragment that we're thinking as our example, we construct our active space in the way that I've described, or otherwise, and then we do our strongly correlated level of theory on our active spaces we've constructed. We explicitly consider the electrons, the interactions between them. They open up some kind of Coulomb hole between the electrons, and that's good. And that gives us our description of our strong correlation in our active space. And then you might want to do sort of perturbation theory on top of that. But what we're neglecting is the interactions of the electrons in our active space with all of the electrons outside it. And those interactions will perturb the electrons outside of your active space, and that will set off a chain of essentially density fluctuations or polarization bubbles in the environment, which have a systematic back reaction back on the electrons in your active space, right? And that sort of physics is completely missed. And what's very clear from this little very much cartoon is that this physics is not simple second order bare perturbation theory, right? In a kind of more condensed matter physics perspective, these would be called retarded or screened interactions, right? And they're many electron processes, right? They are they're not pairwise. They involve chains of polarization of electrons in the environment. And crucially, as systems get larger and band gaps get smaller, this is the dominant many-body effect, right? If you look at something like the high density limit of a uniform electron gas or something like that, this is the RPA, the random phase approximation type physics that is the dominant many-body physics and is not captured by kind of a bare second order perturbation theory. And one way to think about this, if you were kind of to think about what the effect is on the active space that you're describing, this is a reduction in the effective Coulomb strength between your electrons in your active space. And so you can think of it as kind of an electronic solvation effect, which is quite a nice way to think about it. But there are essentially large many-body rearrangements of the electrons in the environment to actually reduce the effective electron strength, the effective interaction strength in your active space. But crucially, this is also energy dependent. It depends on the kind of energy scale of the scattering events in your active space. So can we reformulate quantum embedding to take this into account from the start in a kind of perturb-then-diagonalize type approach? I see I'm running out of time, so I'm going to very much skip this. The idea is we want to take a Schmidt decomposition type approach. We want to describe some global state, which should be the RPA state, which has this kind of physics, then truncate it in the same sort of way in order to calculate a kind of bath degree of freedom that we can include in our active space and then perform the strongly correlated physics. Now, skipping the details, the kind of the outcome, if you follow this through, is that actually the bath degrees of freedom that you need to augment your active space with, these environmental fluctuations are actually bosonic-like in their character. Now, this is a bit weird, and this is where it really goes outside the kind of domain of sort of the traditional multi-reference perturbation theory approaches, but it is all rigorous, and it is all following through the standard approach of saying, I want to be able to capture the long-range RPA physics, this perturbative physics, in my active space and then do the strongly correlated physics. So this is an algebraic approach that provides bosons describing long-range quantum fluctuations between your active space and its environment. Difficult problem then, and this is something we're working on, is that then you need your active space solver to be able to describe coupled electron boson systems. Now that is quite a hurdle to get over, but is not a fundamental limitation. It does make things a bit more complicated, but there's no reason to think that we can't think of active space solvers that describe both electrons and bosons on the same footing. The bosons describing these long-range collective fluctuations. An alternative perspective of this approach is that it's a self-consistent random phase approximation with local exchange and correlation to all orders in some local active space. Another way to think about it is that this is a perturb-then-diagonalize multi-reference perturbation theory that doesn't involve high body density matrices and has an infinite diagrammatic resummation in the external space. So yeah, I'm going to skip that. We are working very hard, and I was hoping to have an ab initio implementation for you to describe what's going on, but we haven't quite got there yet. We're still working on kind of parameterized type PPP models, Huckel models with correlated physics. And kind of long range 1/r interactions, and then we can kind of look at models of these kind of conjugated Coronine derivatives. We can take our local active, our local sites, we can construct our active space, we can do RPA, and we can calculate these bosonic portions of the active space, and then we can calculate energetics and things like optical absorption spectra and optical gaps, and you can see that we can reduce the error of something like the parent random phase approximation down to something a much smaller error. So this is looking across a range of different systems compared to very accurate multi-reference CISD methods. So I'm going to have to stop there. I do have other slides and other results if people are interested, but I'd like to thank you all for your attention, and I hope that the talk was of interest. Thank you.
Thank you very much, George. We have time for one very quick question. John.
Thank you very much. George, amazing talk, always inspirational. So I have a question that I hope to give you a couple of more minutes to expand on this topic. So
Sure.
you have been talking about the fluctuation, local fluctuation of, let's say, charge, electron, correlation, so on and so forth. how would you put the long-range spin coupling that you had, for instance, in a one-dimensional chain into this framework?
That's a great question. That's a great question. The key, okay, the key point why spin physics is not in the scope of what I was talking about, right? So what I was talking about here, and I don't know whether you were talking about the first part or the second part. In the first part, this is just a way to construct an improvable active space. So if you can converge the range of that spin physics, or you can describe it as in the broken symmetry of a mean field that you start with through some self-consistency, then that will capture your long-range spin physics. So that's, you know, that's from the first part. From the second part, what I'm describing here is charge fluctuations, not spin fluctuations, right? So I'm describing, I guess, from this picture, I'm describing sort of density fluctuations, not spin fluctuations. Now you can describe kind of RPA for kind of that kind of spin type physics. We're then essentially not looking at a resummation of bubble diagrams in RPA. We're looking at a resummation of ladder diagrams that describe essentially the coupling of a spin operator with another spin operator and chains of those spin operators. So if you wanted to develop a multi-reference perturbation theory for capturing spin physics, you would have to reformulate it for a particle-particle RPA, or for the spin physics for the ladder diagrams. Now that can be done. It's not really where I'm going. It's not the it is of course important physics for a lot of spin systems. It's not the most important physics if you want to describe things like long range density fluctuations, plasmons, or things as your band gaps get smaller and you get very polarizable systems in terms of the electron density rather than the electron spin. So yeah, it's a great question. It's something outside of the scope of what I talked certainly about in the second half of this talk. In the first half of the talk, it would have to be captured in the kind of mean field or the self-consistency of the approach.
Great answer, thank you.
All right, so let's thank George again.